Welcome to our 11:30 press conference. Sorry we're running a little bit late. This press conference is about the 2014 South Napa earthquake, and we'll have two speakers who will speak in this order. Julian Cohen-Weber, he's a PhD candidate in geotechnical engineering at UC Berkeley. And Ken Hudnut, he's a geophysicist with the U.S. Geological Survey in Pasadena, California.
Thank you all for joining us today. Let's see if I can. All right, so I'll be discussing the performance of structures in a densely urbanized environment in West Napa specifically, as affected by surface fault rupture during the South Napa event. I'd like to acknowledge my co-authors, Drs. Bray and Dr. Sitar, and my classmate Robert Lanzafame. The full version of the Geotechnical Extreme Events Reconnaissance Report is online, and I invite you all to go visit it. I'll have a link for that at the end of the presentation as well. I'm also presenting a poster on surface fault rupture tomorrow afternoon. So I'm not going to go too much into detail about the South Napa event. I'm assuming everyone's heard a little bit about it, but suffice to say that this is the first occurrence of surface fault rupture in Northern California since the 1906 San Andreas event. It's also the first occurrence in Northern California of surface fault rupture in a densely urbanized environment. So that's important. The questions are, what would we expect given the next big event? And what does this event tell us specifically about the interaction of the urbanized environment and surface fault rupture? And are we prepared? As you can see from the images here, it's a pretty complicated environment. In this case, you can see the left photo. The surface fault rupture ripped straight through the street towards the house on the left, and then just jogged to the right, barely nicked the corner of the garage, but went straight through the house on the right, shifting it 6 centimeters on the foundation and resulting in severe structural damage to the foundation. The current standard of practice, generally speaking, for mitigation of the surface fault rupture hazard is avoidance. We have legislature on that, the Alcoa-Priolo Act of 1972, which essentially requires a 15-meter setback from active faults for human occupancy structures, unless proven otherwise. But we also know that surface faulting is very much affected by different fault characteristics. In this case, we had a strike-slip fault, so the behavior is specific. The overlying soil, if it's a ductile soil, for example. And then, of course, the foundations and the structures that are at this ground surface. Realistically, I think it's important to acknowledge that the effects of surface fault rupture can be acceptable or unacceptable in an urban environment, depending on the actual structure and the design. I'd like to note that the Alcoa-Priolo Act is presently under review by a technical advisory committee. And so it's important that we're making progress with all the data that we're getting. So what did the South Napa event show us? We went out in the immediate aftermath and performed detailed mapping of 27 single to two-story wood frame structures. I should say that these are all residential structures, and we really appreciate the cooperation of the residents in these neighborhoods, and we really appreciate your consideration in their privacy. So we collected a very comprehensive record of the seismic damage. We took measurements, photographs, and then performed a qualitative assessment in comparison of the structural performance of the different failure modes that we observed. This is just an example of, you can see on the left, the trace of surface fault rupture. The turquoise box delineates the area of the houses that we mapped in detail. And then there's a close-up just to show you just how sinuous this surface fault rupture is. So it's pretty complicated. We saw 3 different types of structures, generally speaking. with regards to their foundation. The first was the very standard shallow spread footing foundation, which is common to construction in California. These structures generally experienced through-going surface rupture, and simply because these shallow foundations are shallow and allow for a relative decoupling from the ground surface. So they kind of shake at the ground surface back and forth. Unfortunately, these foundations are also, they lack a little bit of rigidity. So what we saw was a lot of angular distortion of the structures above that. In this case, you can see there was a garage that kind of settled about 5 centimeters to the west. And then you can see the close-up of the cripple wall and foundation beneath the house where the red star is. The foundation was cracked straight through, and the cripple wall essentially created a soft story in a sense, and the whole building shifted. And that's all a result of strong shaking, obviously. The second type of structure that we saw was the structures on pier and grade beam foundations. So we're talking about a deeper foundation, and the structure is literally anchored to the ground, creating sort of a stiffer structure. So this deep, stiff foundation kind of forced the rupture to the edge of the buildings or directly towards weakness within the structure. So what we saw and what we expect in this is that this kind of foundation does not accommodate for much differential displacement. It's anchored to the ground. So if the surface fault rupture progressed through the building, what we saw was that it really sheared the building. There's an example here of the rupture trace proceeding through beneath one of the buildings, and between, you can barely see the pier foundations at the top of the photo. And you can see examples of the structure itself kind of being sheared apart, where we saw a roof beam detached from the walls and a lot of cracking in the hinges of doors. So the whole building was sort of shifted. So all in all, the significant structural damage that we observed, I think it's important to recognize that was directly related to the actual rupture itself. And in the areas set back from the rupture, you saw much less damage in comparison. We saw that light wood frame structures perform very well. They are flexible. That's why we use them in California. So that's another reassurance that our construction isn't that bad. New construction performed very well. We saw a recently seismically retrofit structure with a reinforced mat foundation and moment frame, which took the brunt of the surface fault rupture and spread it out around the building. The building experienced very little damage. And as I said, structures on shallow spread footings, which were relatively decoupled from the ground, experienced angular distortion because of the shaking back and forth, and the relatively flexible foundation allowed for that angular distortion. Structures on pier and grade beams are much stiffer and sheared with the differential displacement. This is an example, an 11 centimeter offset on the bottom left of a house on shallow footings. So I asked these questions. What should we expect of the next big event with respect to surface fault rupture? Well, we can expect many of the same modes of failure and structural performance, but to varying degrees, naturally, depending on the fault, depending on the amount of displacement. What does this tell us, and are we prepared? Simply put, yes. We have a system that works, and the aqueous Priolo and the state of practice serve their purpose well. But it's also safe to say that ground movement due to surface fault rupture can be analyzed and mitigated as for other ground movement hazards which we currently perform, such as landslides, subsidence, lateral spreading. And so safe design is possible in these hazardous fault zones with the proper considerations, and that's land use planning, appropriate site characterization by engineering geologists, appropriate foundation design, decoupling the foundation from the ground by geotechnical engineers, and then allowing for some flexibility within the structure itself by structural engineers. So with that, I'd like to invite you to visit the full report, which was a very collaborative effort with quite a few folks. at Gear, the CGS, Pier, and the USGS. This work was funded by the NSF, and we really appreciate it. Thank you.
Great. Well, I'm Ken Hudnut with USGS, and I'd like to introduce to you another report. This is just recently released. This is from USGS to FEMA. So there were some particular aspects of the earthquake and its impacts that FEMA gave USGS a mission assignment task to complete on a very short timeline. So over the course of the past month and a half, we completed that report and then delivered that to FEMA. So I'll just take through and focus on the same area that Julian was just talking about, the neighborhood in Browns Valley, and in particular the fault afterslip. So I'll just take a moment and explain what I mean. The fault moved at the time of the earthquake, but then it has continued to move at a steadily decreasing rate. And so this is a phenomenon that we're quite familiar with from other earthquakes, but this is the first time that we've really had to cope with that intersection of fault afterslip with a residential community. So as Julian mentioned, we don't often get earthquakes that cause fault rupture that goes through a neighborhood, as it has in this case. The 71 San Fernando earthquake, otherwise known as Silmar, is another one to mention there. That, in 1971, produced up to 6 feet or 2 meters of fault movement right through a residential area. And there was some afterslip, but it was not as pronounced as what we're seeing in this case. So for a magnitude 6 earthquake, the South Napa earthquake produced a very large amount of surface rupture, and it produced afterslip, which is most pronounced in the southern part, but is also significant in the Browns Valley neighborhood. That's why FEMA asked us in to take a special look at a high zoom level on the Browns Valley residential area. So this report, we are officially announcing it here and releasing it. It's available on the web. At the end of my talk, I'll show you the URL for that. The handout that Leslie Gordon has also has the URL for the report. It's a 4-part report addressing each of these key factors that FEMA requested USGS to work on. The request actually came to FEMA from the state, so that's the way the National Response Framework works. The state requests the work be done, FEMA supports the other federal agency to do it in this case, and we completed our report. So it's a loop where the idea is to have requests for support by the federal government driven from the local and state agencies, and then result in work in support of the local and state agencies. So on the 4th of December, we delivered this report, presented it to FEMA and Cal OES at the Joint Field Office. We then, last Friday, December 12th, delivered that same report to the City and County of Napa at City of Napa City Hall. And today, we're publicly releasing this report here. So the 4 parts are afterslip in Browns Valley. We are issuing a forecast for the afterslip over the next 3 years. We've used alignment array data, LiDAR data, and are continuing to work on refining our forecast. But at this time, we're presenting the forecast to the best of our knowledge, but we will be continuing to get more data and refine the forecast. Second part of the report, these next 3 parts I'm not going to present here today, but they're in the report. We did an assessment of shaking amplification in the downtown City of Napa area. We looked at fault hazards in the longer term. That's work that we're going to be conducting over the next several months, in particular in conjunction with CGS. And then we also are supporting the needs of the emergency managers where it comes to geospatial intelligence, or imagery, in other words. And so these are aspects of work that we're doing as well. So just to start right out, this is from the executive summary of the report. We're looking at the same area that Julian just showed you up at the northern part of the surface fault rupture. And what I'd like to point out is, the pointer here, from letter A up to letter B, you see we've colored this portion of the main fault strand yellow. And there's a legend down here at the bottom which explains that that means that over the next 3 years, we expect from 5 to 15 centimeters, or between 2 and 6 inches of continued fault afterslip along that yellow portion. So where Julian just showed you the damaged house is just right up here. And so A to B, yellow, is that moderate afterslip hazard. All the other lines that you see here are colored green because we forecast that they each will experience less than 2 inches of afterslip over the upcoming 3 years. And so red, you see there's nothing colored red here. That's good news for people. In future earthquakes, for example, a magnitude 7 on the Hayward fault, for example, we might very well have a lot of fault line showing up in red using this legend here. So what we tried to do is come up with an assessment for the South Napa case, but also in this report, come up with a new scheme whereby we categorize the level or the severity of the fault afterslip. And so although there's no red shown here, the idea is we've hopefully created a tool that will be useful for future earthquakes as well. So A to B on the map that we just looked at, we'll come back to the map to remind you, but that's on the southern part of the main strand of the West Napa fault system within Browns Valley. Going from Partrick Road to the north in Browns Valley, C to D on the map, I'll point that out when I show it next, experienced no significant afterslip, and so we assessed a low afterslip hazard there, as well as on the eastern strand, which did break co-seismically at the time of the earthquake, but that did not show afterslip. And all of the other fault strands that go through the residential area of Browns Valley, many of which had not been previously mapped, some of which had been previously mapped, all are colored green on the afterslip hazard map to just indicate that we see no indication of a moderate afterslip hazard. We colored them green because we see those as having a low afterslip hazard. So although the forecasted afterslip along that yellow section is moderate level and it poses an ongoing hazard to structures, as Julian just showed you, the structures were in many cases able to accommodate the co-seismic slip, but this is the afterslip, and so an additional amount of fault movement will be impacting these structures. So the idea is to provide guidance through FEMA and CGS and Cal OES to the local agencies who need to decide whether to allow homeowners to repair their homes and move back in. And so the afterslip is part of this bigger picture about the threat, not only the co-seismic slip, not only the afterslip, but also the threat from future earthquakes, which is a very important part of this bigger picture. So Julian mentioned the Alquist-Priolo Act. I want to mention it again right now and say that coming back to the map now, I'll skip back and come back to it again. Several of these strands had been mapped previously, but were considered potentially active faults under the definitions in the Alquist-Priolo Act. Tim Dawson is here from CGS in the back wearing the vest. That's Tim. And so the state has the Alquist-Priolo Act and the responsibility for mapping the active faults. So several of these had been previously mapped, but these did not experience much if any co-seismic slip and are not having any afterslip. So the main fault rupture came up strands that in some cases had been previously mapped but were not assessed to be active faults under the Alquist-Priolo definitions. So this is something during Q&A maybe we can explore further with Tim Dawson's input. I should mention too, Ann Rosinski is sitting next to Tim. She led the California Earthquake Clearinghouse after the South Napa earthquake and facilitated bringing in this tremendous wealth of information that was then summarized in the GEAR report that Julian mentioned and also the EERI report. So Ann Rosinski is also with the state. And so all of this tremendous response, all of this new information that we've gotten and then summarized in these reports is through the California Earthquake Clearinghouse, a very important part of earthquake response in California. So I had mentioned already A and B, and we talked through C to D on the main strand and E down to F on this eastern strand. Those are the parts of the fault system that broke with quite a bit of slip in the South Napa earthquake. These other secondary strands, some of them are only known to us now through co-seismic imagery from airborne and satellite synthetic aperture radar, for example. I'll show one example. and then these had been previously mapped. So the green lines on this map are a collection of different types. I wanted to keep moving through the material here and allow time for question and answer. So how does the afterslip that we're seeing along the West Napa fault system compare to afterslip elsewhere and from other earthquakes? We've seen afterslip after a number of California earthquakes. We don't see it every time. So for a magnitude 6, as I said, it had a lot of surface rupture and it's experiencing a lot of afterslip. One thing that's different is we're seeing a lot of afterslip in the southern part of the surface rupture, but the afterslip was very sudden at first and slowed down very quickly. So I say here, the fault hit the brakes surprisingly fast. We've seen in other examples of California earthquakes, we've seen that the afterslip has a longer time constant. So this is a sudden decline in the rate of afterslip. So that's something that makes us think when we use future extrapolations that are based heavily on data from prior earthquakes, we need to be careful because this is a different case. We also know that in the first few months since the South Napa earthquake, this fault has been creeping faster than any other fault in the world, at least where we can see them on land. So we know the San Andreas has the creeping section where the rate is up to 3.5 centimeters per year. The Chinchang fault in Taiwan in the longitudinal valley is another one that it creeps at up to about 3.5 centimeters per year. These have been well known for a very long time, and these are driven by the mostly steady tectonic rate across the plate boundary. In cases with afterslip, it's a low friction fault, and at the time of the coseismic slip, it loads the upper part of the fault, and that part then creeps. And so this is a well-known phenomenon. So we've seen it many times before, but as I said, this has slowed down surprisingly quickly. So an overview of the surface faulting. Julianne showed you some of this. This is from the report, and it's a new figure that summarizes the data, the full compilation of the data a little differently. So this is work by Dan Ponte, Carlo Rosa, and others, and Tim Dawson and others also contributed heavily all the data that went into this. So in letters and numbers that are probably a little too small to see here, you can see slip numbers summarized. This is in the report, so I'll encourage you to look there. But just, I'll mention it from the map view here, and then I'll come back to it and show you in a different way. But from the epicentral area, the epicenter is the red star at the south end, down near Cuttings Wharf. The rupture went northward, and it also came up dip. So you've probably heard that, how the rupture propagated toward the city of Napa and came up dip, and so that directed more energy toward Napa. But the rupture propagated towards the northwest, and the maximum slip coseismically was up in here. It then went through Browns Valley with about 12 centimeters of slip in the southern part, and then this eastern strand had 6 to 8 centimeters on it. So the biggest slip, though, is down in the southern part, and mostly that has accumulated as afterslip. So we're going to start at the south, down near Cuttings Wharf, and move north quickly. This is actually about midway up at the Clodoval Vineyard, and what you see here, the fault is coming across a pre-existing scarp, diagonaling across this image. And what you're looking at are vineyard rows that were originally planted straight, but that are jogged a little bit right through the center here. I hope you can see that with your eye. But for us, this was about as exciting as it got. We drove through with the truck-mounted laser scanner that Ben Brooks and Craig Glennie have developed, scanning and scanning, and suddenly we were actually able to see these offset rows. It was rather stunning at this one location that we could see it, partly because of the foreshortening. We were looking up this little hill. But the fault rupture going through here, you can see the rows offset. Here, the offset is about 25 centimeters, and in other places it was up to about 45 centimeters. But it was rare to actually be able to see the vineyard road offsets. Here's another case, similar looking perpendicular to the fault, in this case farther up the fault along Buman Ave. But you see at the notebook, the fault rupture goes through the picture this way, and the fault was, the fence line was originally straight, and the fault offset it, in this case by about 18 centimeters. So that gives you an idea of what the fault rupture looks like out in the field, where it offsets vineyard rows and fence lines. And here, a little farther north along Buman Ave, the rupture goes through Atlas Vineyard, and this is an avenue along the side of the vineyard, where the slip is about 45 centimeters here, near the maximum value of slip. And here you see what we call on-echelon fracturing. And Julian showed examples of how this on-echelon fracturing stepped across the asphalt in the Browns Valley residential neighborhood. So going northward along the fault just a little more, we'll see that. First, I wanted to show this figure. So Cuttings Wharf on the right and the epicenter down here at the south end. Where we just were looking is along the southern portion of the fault, where most of the coseismic slip, actually most of the total slip was not coseismic, but rather post-seismic. So this is all from observations made by Jim Leinkemper of USGS from the alignment arrays. The dark gray curve, the lowest curve, is the coseismic offset. And then within just a matter of hours, we saw this rapid afterslip in the south, which kept building up more and more slip. This was most noticeable at Highway 12, which is right here. But in the southern part of the fault, the afterslip was rapid and sudden, and then it also tailed off quickly. The maximum slip was in the area where I just showed you those photos up along Buman Ave. And then north of that maximum slip, where there was very little afterslip, is where Browns Valley is. So this is the residential area right up in here. Between NLOD, that's Leaning Oak Drive, and Redwood Road here. So this particular area, and what we're seeing here is that the afterslip isn't quite as suddenly dropping off, and yet this is where we need to forecast it most accurately. That's where the houses are. So we're going to zoom in on that, just as Julian did. Again, this is Browns Valley. You see here, now you can read the letters and numbers, going from about 12 centimeters at the south end near Leaning Oak Drive up through the White Cliffs residential area of Browns Valley, 11 centimeters there. And then on the main strand, the slip dropped off. On the eastern strand, the coseismic and afterslip was 3 to 8 centimeters there. So, or I should say, I should correct myself. On the eastern strand, we have not seen any afterslip. So those numbers represent only coseismic slip. So just as Julian did, we're going to zoom in a little bit more now on the same section of the southern part of Browns Valley. For reference, again, this is the yellow portion of the afterslip forecast map. And this is what it looks like. Julian showed you this figure already. And on the right, we're going to combine in a little bit of data about real estate values. This is just taken from Zillow. We've since used the county assessor's office data as well to fine-tune our initial estimates. But basically, we want to put it in terms of dollar numbers. What's the impact here? This is the red tagged house you'll see there. See that again. But see, these houses not only had the coseismic slip, but also the afterslip. So after 3 months, we're right about at this point in time now. And this is like any kind of a forecast where you need to take the data that you already have in hand and then forecast out into the future. So one simple way to do that is using data, and based on a lot of these other prior California earthquakes, we can forecast out using this program called After, which was written by Jack Boatwright, but based on a lot of data collected by Bob Sharp and others for the Imperial Valley and Superstition Hills earthquakes down in the Imperial Valley, where we have a thick sedimentary stack, kind of a different situation than up here in South Napa. And then these upper curves that don't flatten as quickly are from an Omori and modified Omori curve. So these are just a 1/T time decay, a simpler form, and those project out higher. So when we look at that yellow line and say in the next 3 years, the afterslip is forecast to be from 5 centimeters up to 15 centimeters, the lower projection range is from this curve and the upper range is from these. So that's the nature of the uncertainties we're looking at. So we have the formal uncertainties, but also the epistemic uncertainties that we're trying to take into account, and these are described in the report. So you can see how, with the data that we currently have in hand from the South Napa earthquake at the Leaning Oak Drive alignment array, which is at the south end of Browns Valley, this is what the data look like, and that's what the curve fits look like. And we can actually project out even farther into the future beyond the 3-year timeline, and there's some mention of that in the report. From the NASA JPL UAV SAR, this is the Airborne Synthetic Aperture Radar, this is what the pattern of afterslip looks like through Browns Valley. This is the Leaning Oak Drive alignment array here, and you can see how the main strand of the fault is continuing to have afterslip. The dates are given here, August 29th through October 22nd. it starts to fade a bit as you get up into the White Cliffs area, and then it fades out entirely by the time you get up to Partridge Road. And so that's why on the Afterslip forecast map, it's green from Partridge Road to the north. So I just wanted to share with you and show you some of the actual data that were used as the basis for the forecast. So again, just to review, there's the forecast map and the meaning of the red, yellow, and green. And so this is all in detail in the report. So just briefly, what is the value of this Afterslip forecast map? Well, we try to put it in terms of the impact on the neighborhood there. If you were to sum up the property value of all 1,800 homes shown on the map, that's about $1 billion worth of real estate. Of that amount, the fault lines shown in either green or yellow on the forecast map add up to about 200 homes, or about $110 million worth. And of those, the houses on the yellow line are only about 20, and so that's about $10 million worth of real estate. So it's a small percentage of the properties in Browns Valley that were impacted directly by the fault rupture and that have the moderate level of afterslip forecast. So anyway, this is what we're working with now with the city as well as other agencies, and I think, as I said earlier, the bigger picture in terms of hazard for these homes is really not only the co-seismic and afterslip, but also the future earthquake hazard. And that's really the role of the state, CGS, and the Alquist-Priolo Act. They'll be later releasing revisions to the Alquist-Priolo Act maps for that whole area. So as I mentioned, the USGS open file report, that's now available at this URL. And so here also, Julian and I are here to tell you about the upcoming special sessions about the South Napa earthquake that will take place beginning tomorrow. In particular, the oral session in Moscone South, room 307, from 8 a.m. till 10 a.m. And then in the poster hall, the posters in the afternoon. These are the session numbers here. I hope you'll take a note of those. And then I hope we've left enough time for question and answer. Thanks.
Okay, thank you, speakers. We'll now open the floor to questions, and David Perlman will start.
Yeah, I'm Dave Perlman from the Chronicle in San Francisco. Hi. First of all, quickly, you've already answered the question. All of that text material, is that included in this open file report as well? Those slides that you showed?
Yeah, one thing that's not included in the report is the real estate value assessment. That's more just work in progress, not exact numbers. So that's not included in the report.
Okay. Well, I wonder if you can give us a brief introduction into the cause of co-seismic slip and after slip. Why is it? You mentioned the fact that it's related to the tectonic regime in which we live, but in what way or how does it, the crashing of two seismic plates, tectonic plates rather, how does that generate after slip, such as the stuff you described?
It's a type of material like fault gouge is one thing you've probably all heard about. Material that creeps is, it has special properties. It's lower friction material, but it also is, I'll make sure I get this right under the gun here, but it is slip strengthening material. So what happens is deep on the fault where you have rock on rock in contact, that material slips quickly in what we call stick slip. So you might have a friction of 0.4 down there where it's rock on rock. And then in the upper part where you have, let's say, more like mud on mud, that at the time of the earthquake absorbs the slip that's coming at it from down below, and then it releases it gradually through time. So it's like a spring and dash pot model where there's an impulse at the base from that rapid slip of a large amount, and that goes into this material up top that has very different frictional properties. You put stress into that upper material, and then that stress gets released gradually with time. So initially very rapidly, and then that tails off with time. So we then fit a time decay curve to that. So it's a very interesting phenomenon. You've heard for many years, I'm sure, about how we forecast aftershocks. But really, aftershocks are pretty hard to forecast accurately. You notice we don't say the exact magnitudes or locations or times of aftershocks because that's very difficult to predict. But here we're issuing a forecast and we're essentially predicting what the afterslip will be. And you know how cagey we are about predicting anything when it comes to earthquakes. So I think this is an unusual case where we feel like it's such a slow, steady process, and we've seen it happen many times before, that we feel reasonably comfortable issuing this forecast.
Excuse me, Harvey Leifert, freelance. For us out-of-towners, could you review this act you keep referring to?
I am going to toss this question to Tim Dawson because he's actually head of the Alquist-Priol Act for the state of California, and since he's in the room, I hope maybe, Tim, you could take that question. We had a feeling that questions about the Alquist-Priol Act might come up, and Tim's the perfect one to answer that.
Yeah, just in general, what the Act says, it came about because of the 1971 San Fernando earthquake in Southern California, and it was recognized at the time that the one thing you can do to mitigate for surface fault rupture is to actually set back from it. And so what the law requires is the state produces these Alquist-Priol zone maps where we go out, we map these faults in detail, and right now the criteria for that is we're interested in faults that are sufficiently active and well-defined, so faults that can be mapped by a trained geologist as well as sufficiently active, which means that they've had activity in the last 11,000 years, so basically Holocene active faults. Those are the faults that, by law, when they're zoned, they require geologic investigations within those zones that are established by the state and the state geologist. And so if you want to develop within one of these zones, someone will hire a geologist, and they'll do studies within those zones. They'll do mapping of the faults at the surface as well as subsurface mapping, usually in the form of trenching, paleoseismic trenching across that. They establish where these faults are, and then the consultants who are doing this work will make recommendations about how far to set back from these active faults if there are faults identified within their investigation area.
One thing I should mention is I didn't show a slide for this in the interest of trying to keep remarks shorter. In the report, there are some initial findings from the California Geological Survey about one of the strands of the West Napa Fault system. So trenches that were opened for the purposes of trying to ensure that a development would be done safely, the consultant working on that project made the trench walls available so that CGS and USGS folks could get in and study that. So there's a very interesting part of the report that addresses the fault hazards question, but the sediments that were offset by prehistoric earthquakes have not yet been dated, so that's work in progress. So I think this is something the whole topic of fault hazard is clearly going to be important as people try to decide whether they should repair their home and move back in. And so the enforcement of the Alquist-Priol Act is done by the local agencies, and in this case, CGS, we're working with the City of Napa that have the authority to just decide whether or not to issue a permit to repair a house, knowing that it's in a fault zone and having afterslip.
Do we have any more questions from reporters?
Craig Miller at KQED. In the immediate aftermath of this, the nomenclature of where this actually broke was a little murky. We heard West Napa Fault. We heard an unnamed or unmapped sort of spur in the West Napa Fault zone. Your references to the southern segment of the main strand of the West Napa Fault, is that what we should settle on for where this actually happened?
Again, I would turn to Tim on that. The state will have, final say in the naming. We've tried to use the same system that they have used, and in our report, we've gone with a particular convention. But Tim, can you say whether that'll be used in the final analysis?
Yeah, I mean, the fault itself is fairly complicated. That's why we've been referring to it within the state, and was referred to previously by the USGS and their quaternary fault and fold database as the West Napa Fault Zone. And what that is it's a series of subparallel fault strands that we think are related to each other. And so from the state perspective, you know, we previously had an AP, one of these AP zones on the southernmost part of this fault zone where it was well defined in the area of the Napa County Airport and American Canyon. But as you head north from that area, the fault's actually several strands, and that's why we've been calling it a fault zone, in terms of they're somehow related to each other, but they're individual smaller faults within that fault zone.
So in our reporting, how should we refer to where this actually?
I would say the West Napa fault zone.
One thing that comes up in that question is the width of the deforming zone, and this is very important, of course, to assess future hazard. I mentioned about how it was surprising to us that for a magnitude 6 we had this large amount of surface rupture and this amount of afterslip. But another thing that was also surprising, maybe not quite as surprising, was just how many fault strands broke at the surface. You know, so it was a complex rupture. You know, unlike the 2004 Parkfield on the San Andreas, which had afterslip that behaved somewhat like what we see here, unlike the Superstition Hills or Imperial Valley where we saw afterslip, in this case we had surface rupture co-seismically on several subparallel fault strands and then afterslip on just the main strand. So, you know, we're learning a lot from this earthquake. I want to emphasize too that we're not only zeroed in on the fault afterslip forecast. That's just what we happen to be, you know, announcing with this new report. But tomorrow with the talks and the posters, I think if you're able to go, you'll see a lot of really exciting new science. And also it's this intersection of the science with the engineering geology, like what Tim represents, and the structural engineering, as Julian showed in his remarks, and what's mentioned a lot in the GEAR report that he talked about. So it's really a very practical thing of how this rupture broke and then has continued to move right under people's houses here. And then I think another way to broaden this, and this is maybe overreaching a bit, but what we've had revealed to us here is that this could happen after, say, a future magnitude 7 on the Hayward Fault. We've talked with you all before about this scenario called Haywired. So a 7 on the Hayward Fault. The Hayward Fault creeps normally in between the times of earthquakes, and so we have a feeling that the frictional conditions on that fault are comparable to what we're seeing here. And so we would also expect afterslip to occur after a future event on the Hayward Fault. It doesn't even have to be a 7. You could have a 6 on the Hayward with a whole bunch of afterslip, and it could be very disruptive. We could have, as I said, a lot of red, high-severity fault afterslip in a case like that. And this is not wild-eyed stuff. This is something we can be pretty sure about. Just one other thought before we end things here. As Tom Broker, the director of the Earthquake Science Center, who's here, mentioned and made sure we put into this report as a kind of disclaimer, we see what's happening with the afterslip, and we have forecasted it on the basis of what we see up to this point in time. But it's possible that we could have a large late aftershock. Aftershocks are to be expected, and if there's one large enough and in a place that could affect what's happening here, that could really change things in terms of the afterslip. So if a large aftershock were to occur, we will reevaluate and take a look and see if our forecast for afterslip is going to hold or if we need to reassess and issue an update to the forecast.
Harvey Leifert, one more question. Sorry about the voice. Has there been any effect at all on the wine industry in the Napa Valley? Or are the vintners worried in some way because of what happened and what could happen?
I'll say that there was a big impact on the winemaking community. So many of the vineyard owners and managers allowed us to come into their properties and do our laser scanning and so forth. So we got to meet them, and they've allowed Tim to go in and do trench excavations to study the past earthquakes. So they've been, I want to thank them too. Julian did also thank the residents of Brown Valley, but just the kindness of people to allow us in to do our research. It's been so important to us to be able to do our work, and it's been great making friendships with these people and talking with them about their experience in the earthquake. The fault rupture was disruptive to their business. So if you look at the overall damage from the earthquake, it's approaching 400 million is my understanding, and could go even upwards from there. You hear numbers as high as $1 billion in total damages. And of that, I believe the number is about 80 to 100 million in damage just to the winemaking industry. And so, of course, tourism is also very important in Napa Valley. This earthquake occurred not long before the Labor Day holiday, and so they were concerned about the tourism numbers. Actually, they were able to get back on their feet so quickly that the tourism actually did pretty well, as I understand it. But there were impacts to the winemaking industry, such as the large 10,000-gallon stainless steel tanks in some cases were damaged and had to be replaced. This damage occurred right before the crush, so the grapes were ripe and ready to be picked, but the earthquake just set back the time schedule for that for certain operations. And so I would say they've been able to handle it, but they've needed some assistance through FEMA and the state, Cal OES. And so we've learned a lot about the various different aspects of their business. Agribusiness in the state of California is exceeding over $36 billion a year nowadays. So winemaking is just one part of that, and it's not a big part of agribusiness in California, but whenever we can learn something new about potential future earthquake impacts on agribusiness, we try to keep our minds open to that and anticipate what bad things could occur in the future. The winemaking industry in Napa is concerned about the impact that they've had relative to other competing areas, so they want to remain competitive, of course, and they want to remain the focus of a lot of tourism as well. One of the things you probably saw was about the racks where they put the oak casks for aging and how they tipped, and then it was like dominoes, so they tipped but didn't tip over everything. And so they had to go in and take the casks out one by one, and it was actually these, the winemakers themselves got in there and were by hand plucking the oak barrels off. It's very dramatic because it was like what's the game, Jenga? I don't know if I pronounced it properly, or pickup sticks. But if they had made a wrong move, the whole thing could have tipped and a bunch more wine could have been broken open because of that. So it was dangerous. And there are videos you can find online that show this procedure that they did to remove the barrels. But people from the winemaking community, I'm sure, would be glad to tell you all about what they experienced. And the afterslip in particular, they've noticed it where their rows were offset, but then the fault continued to move. And they contributed a bunch of wonderful photographs that we were able to use to reconstruct the afterslip. So, and I can put you in touch with some of the winemaking community out there that I'm sure would be glad to talk with you.
Okay, well, thank you very much for attending this press conference. Thanks, speakers, for your interesting talks. Our next press conference will be at 1:30 p.m. on advances in tsunami warning and forecasting since the 2004 Indian Ocean tsunami.